everybody to the last talk of this semester in the Space and Time Beyond the Gravity project.
Looks like she went really small.
Very normally here, of course, she's a member of the Geneva group of the larger Beyond Space-Time project. She did her PhD at the University of Sydney, working under supervision of Hugh Price and Dean Pickles. After having done undergraduate degrees in philosophy and physics, she then went on to do a postdoc at the University of Pittsburgh before coming here to Geneva. Karen has a book published with Springer called Effective Spacetime, which grew out of her PhD work to a large extent. She has publications in various journals, BJPS, UJPS studies, the top journals in the field. She's working in philosophy of physics, philosophy of science generally, specifically, of course, about the fundamental physical theories, their relations between one another, their nature, and how all of this, of course, comes out in quantum gravity. And the current project is focusing on principles and the work of principles in fundamental physics generally and in quantum gravity specifically. That's it for the introduction of the speaker. Let me now turn over to Karen, who will be speaking about when do we stop digging conditions on a fundamental theory. Please, Karen.
Okay, thanks, Chris. So I might be facing that way a little bit because normally I like reading the notes. Apologize for that. So, okay, as some of you guessed, this is the really super thick line in Western Australia. So look at all these layers or different levels here. It's a gold mine, so presumably we stop digging when we believe we can more gold at the next level, or when we believe that we've reached a point where it's no longer profitable to continue digging. So, for instance, if we believe that the resources required are going to outvalue the amount of gold that we anticipate finding at the next level beyond. Okay, so I'm writing this for the FQSI Foundational Question Institute essay competition. It's an annual contest they run, and this year the question is, what is fundamental? Meaning, what does it mean, fundamental? So it's supposed to be written at a level that's accessible to a diverse, well-educated, but non-specialist audience, aiming in the range between the level of scientific narrative and reviewed article in Science or Nature. That's the reason for the one Einstein level today, which I know is a bit different from what normally happens in this series. But please forgive me for not being as detailed and precise in some of my claims as I normally am and what you come to expect. Also, this is work in progress. I haven't finished yet. So please help me with ideas too.
To interrupt, the date has been placed for Chicago. The microphone is not necessarily because the curtain is not pointed to her. And the exact camera. To turn this or shut for no.
It's fine. The microphone a little bit. Yeah.
So, I know it's not really readable, but we're going to kick out since some previous winners. So, last year there were some familiar names. Like this one, Ravelli, Rickles, Ellis, and in particular, the 2008 competition has a lot of big names. Comparative research, Barkeeper, Carol, Karate, and some philosophers. So, I'm going to give it a shot, even though I don't think I'm on the same level as these guys. So my strategy for answering the question is to ask why it is that our current best theories of physics are considered non-fundamental. And this will reveal a set of necessary conditions of fundamental theory. So we're trying to make a checklist of conditions for fundamentality. It will be a further question though whether this list, these necessary conditions are sufficient for establishing fundamentality. So I'll start with a brief introduction. I'll then give an outline of the different conceptions of fundamentality and relative fundamentality in physics. I'll then consider why our current methods of physics are not thought to be. We'll then get this list of conditions, necessary conditions for fundamental theory. I'll then look at quantum gravity and fundamentality claims for the conclusions. So, introduction. It's probably not surprising to this audience, but it's nevertheless a surprising fact that none of our current best theories of physics are considered fundamental. So this is in spite of the standard model of particle physics, our best theory of matter, allegedly proclaiming to describe all fundamental particles and forces. And this is in spite of general relativity, our best theory of gravity, describing what are surely the most fundamental aspects of matter, space and time. So that was the introduction. Now, what do we mean by fundamental? So conceptions of fundamentality in quantum physics have been heavily shaped by the framework of effective field physics, which is a means of constructed theories called effective field theories, which are each valid only at a given level. So at large distances compared to some small scale lambda. So effective field theories are not considered fundamental because they rank.
Oh, shit. Now the Wi-Fi.
Because it may be very accurate, simple, not only captures the relevant physics that you're interested in at the level you're working at. So it presents us with a tower of theories, where each is framed in terms of the appropriate parameters for its level, which represent the important interactions at that level. And these typically do not exist above or below in the tower. Rather than draw a tower, I thought going with the digging metaphor, this is rock strata, so fossil record at the top, got mammals and then dinosaurs, amphibians, fish, and then trilobites. So the idea is that if you study dinosaurs, you can just work at the level of dinosaurs. You don't need to know these other levels, and the dinosaurs don't exist at the other levels. So for this reason, there's a strong case to be made that what is fundamental depends on the level you're working at. Here's the picture in physics. So here in physics, we believe that the stuff at the larger scales, at the top here, depends on physics at the smaller scales, so at the bottom of this ladder. So, and not vice versa. So although we can move up and down the ladder from any level, the idea is that if we want to go, say, from the level of atoms to the level of cells, we can do that without requiring any additional information. However, if we want to go the other way, say from humans to quarks and leptons, we're going to need some experimental data in order to get this. The idea is that the larger scale physics only determines the smaller scale physics. So because of this, there's an asymmetry, and this is why it's believed that the smaller stuff is more fundamental than the bigger stuff. So this is the arrow of increasing fundamentality graph. However, I really want to emphasize this before I continue. There is a strong case to be made that fundamentality is scale independent, as I said. I'm also extremely wary of any in-principle claims. In particular, I'm not convinced that the claim that in principle we can derive any larger scale physics from any smaller scale physics is a meaningful statement to make. But for today, I'm going to assume that it's both meaningful and true. So here are the working definitions. Relative fundamentality. Our shorter scale theories are more fundamental than the larger scale, higher level ones at the top of the ladder, because we believe in principle that these ones contain enough information to make predictions about the larger scale. So then we ask, from relative fundamentality, what is absolute fundamentality? And this suggests that it would be a theory valid at the timeless length scale. Okay. Problem is, though, that according to the framework of quantum field theory, understood as effective field theory, there's an arbitrarily large amount of energy available in the vacuum for the creation of particles. So there's an arbitrarily shorter length scale. There is no tiniest length scale. So we have turtles all the way down, and they're of smaller scales. So the solution to this, of course, is to recognize that we're not trapped in the framework of quantum field theory and effective field theory, as many people have already pointed out. And this recognition frees us from worrying about these turtles all the way down. We can forget about the arbitrarily large vacuum energy. In fact, as we'll see later, we can interpret this as an artifact of a non-fundamental framework itself. So this is the arbitrary large energy is actually one of the reasons for not considering this framework fundamental. So if we accept this, we accept that it's possible that there is a smallest length scale, and thus there's a fundamental theory that describes this scale. However, it still doesn't free us from this epistemic worry. We might think, well, let's keep digging anyway. What's beyond? We never know what theory we're at, whether it really is a fundamental theory. So Darwin frames this epistemic worry as whatever reasons a theory might offer for being seen as final, these reasons must always be based on the theory itself, and thus they can never constitute conclusive arguments against the possibility that a new different theory supersedes the present one and renders the theory-dependent finality claim obsolete. So, turning this on its head, the problem now is that we're not trapped in the framework of any given theory. It says it's final, but we know that we can always step outside of it. I should point out too that Darwin has arguments against the epistemic warrant. He's not putting it forward as an actual warrant. But I'm not going to consider his arguments in this talk because I don't have enough literature. Okay. So, for example, we may find a theory that's UV complete. So it's formally predictive to all possible short distances, meaning that it doesn't break down at any short scale. But this doesn't mean that the theory is correct at all short distance scales. So an example is Newtonian mechanics. It gives us predictions at all scales, but we know that they're not the right predictions. So So even if a theory itself proclaims that it's UV complete, this isn't sufficient for believing its own claims about arbitrarily short length scales, or the tiniest length scale. However, later on I'll argue that UV completeness is a necessary claim for fundamentality. Okay, so now we'll look at why our current best theories are considered non-fundamental. I'll start with the framework of quantum field theory, then particular quantum field theories, including the standard model, and then we'll look at Geneva. So the framework of quantum field theory, there are three interrelated reasons why we don't consider it fundamental. First, it's mathematically defined, which means that the theories it generates are traditionally plagued by divergences. Some of these divergences need to be dealt with in order to render theories usable, and this is done by a process known as renormalization. Finally, the framework is not considered fundamental because although it includes special relativity, it doesn't take into account general relativity. And this failure to include our best physics or more fundamental physics is typically interpreted as the cause of these other two problems with it. So the modern interpretation is of quantum field theory as effective field theory. We have these divergences as artifacts of not taking into account the physics at scales beyond it. So our quantum field theories, aside from being products of a non-fundamental framework, there are 4 reasons why they're not considered fundamental. First is, again, the necessity of renormalization for the theories where it is necessary. Again, we believe that these divergences, these mathematical problems, are due to ignorance of shorter scales than beyond. Also, some theories are not UV complete and thus viewed as vector field theories because they break down at some given high energy scale. And this includes quantum electrodynamics, which is nevertheless a very accurate and highly tested, precisely tested physical theory. And finally, some quantum field theories rely on approximations and perturbation theory in order to solve them. And physicists believe a fundamental theory won't rely on these sorts of approximations in order to solve it. Finally, the standard model is non-unified, which drives many physicists to seek a more fundamental theory beyond. So, even theories like QCD that may not suffer from these first 3 on their own, they're nevertheless not part of a unified framework, and they're products of a non-fundamental framework. So they're still not considered fundamental inside. So now look at general relativity. So the reasons for not thinking that GR is fundamental are the motivations for seeking a theory of quantum gravity. This is a theory expected to describe more fundamental physics underlying the classical appearance of space-time. So the reasons for seeking such a theory include mainly the ideas of unification and requirements of explanation. So first, we believe quantum theory is a universal theory. It says that all dynamic fields must be quantized. General relativity says that space-time is a dynamical field. So putting them together will lead to the conclusion that space-time must also be quantized. And there's also a requirement for a new theory that covers the domains where both quantum field theory and GR intersect, particularly at the Planck scale. And finally, there are some divergences in GR as well. So some particular problematic singularities where the theory doesn't describe, so it breaks down. For instance, black hole singularities and the Big Bang singularity. And so we want a new theory that describes parentheses. Okay. So now we can start creating our checklist of necessary conditions. So based on that discussion, the apparently necessary conditions of fundamental theory are that it be unified, that it be UV complete, i.e. not break down at any short distance, that it be non-perturbative, so exactly solvable, not relying on approximations. It should be internally consistent, modified formally. These suggest a more general requirement that the theory not leave anything that apparently requires explanation. As I'll discuss in a minute, for instance, if the theory is not UV complete, then it's leaving out a section of the world that requires explanation. If it's got these divergences, then we're asking what's responsible for the divergences. So, extending this a bit, some other conditions on fundamental theory are that the background independence, natural, and universal. And I'll go over each of these more closely in a minute. But first, I also want to additionally put some necessary conditions for a theory to be potentially physical. Because we're not talking just about fundamental theories, we want a fundamental physical theory. So I take it that it should not be ruled out by the best experiments, not conflicting with results. It should convincingly link back to successful past current theories in relevant domains. You can see my latest paper on that. And eventually it should make testable physical predictions about the world. Okay, so we'll start with this idea of unification and universality. So, working with a very general understanding of unification here, the slogan is to become one. If we have two apparently distinct theories, unification is when they're revealed to just be different aspects of a more unified, single underlying theory. So, why do we want this on fundamental theory? Well, the history of physics is often seen as a progressive sequence of unification. So we have this idea that it's been successful in the past and the implication that it will continue. Unification is also perceived as explanatory. We can explain these two distinct theories by them coming out of one other theory. Also, the idea is that unification is elegant, simple, it's beautiful, it's parsimonious, etc. But of course, why should the world, or more correctly, our description of the world, be beautiful, be simple, etc., rather than not? So, in other words, why does diversity require explanation rather than homogeneity? Wouldn't it be more striking and more wanting you to, I don't know why, if everything's the same? Because we see diversity all around us. Also, there's no simple understanding or implementation of unification in physics. When we actually look at the history of unifications, different things are typically happening in each of these different cases. Also, I think we can find examples of unified theories, again of different sorts, that were not successful. So pairing these two, seems like unification cannot be linked to success without some further argument, unless you can find something that's linking all the successful unifications, what they have in common that the non-successful cases of unification doesn't have. One thing that it does have going for it is that, at least by putting these two theories together, we know we've got one theory to explain rather than two theories. So we've got less to explain if we have the implications. Okay, so universality is similar, but it's not the same idea. It's the idea that the theory cover all domains. at its given scale. So it's a theory of everything because there's the implication that all large-scale physics is derived from a principle. Universality does not imply unification and vice versa. The first case we could have a mongrel universal theory, so it's not unifying. On the other hand, we could have a unified theory that doesn't cover everything. For instance, electroweak theory. It's not a theory of everything. Okay. So why do we want universality? Well, firstly, I think it's often conflated with unification and its positive aspects, so simplicity, etc. Also, because it covers all physics, there's nothing left to explain at the scale where it applies. However, I can't see a reason for favouring a single theory over a set of theories. Nevertheless, physicists who desire unification, I think, will also want universality in order to maximize its virtues. For instance, fueling environmental energy. Also, I want to say that putting these two together and coming up with which implies that there's a single unified universal theory, it captures something central to the enterprise of physics itself. So, going back to my question before, why does diversity require explanation rather than unity? Well, actually, this is just what physics does. It takes diverse phenomena and then explains them in terms of simple laws. So I think this is part of the very spirit of physics that we have these two things. Okay, so UV completion, again, is the idea that theory doesn't break down at any short distance scale. So this framing of the definition is intended to include non-quantum field theories as well as theories without space-time. They don't break down at any distance scale because they might not have a distance scale. You can question me on that later if you've got a better way of understanding this. Okay, so why do we want this? As I said, if a fundamental theory is not UV, it doesn't describe the tiniest length scale, then we're saying that the world at smaller scales is just not amenable to physical description. So Niels and I call this the UV silence scenario. And it's certainly a possible scenario, but again, I think it's against the spirit of physics to treat this seriously, because what you're saying is that there are parts of the world that are not amenable to physical description, which doesn't seem like something you want to be saying if you're a physicist. It's like you're giving up. In any case, it's not a useful strategy to adopt. Alright, non-perturbative and mathematically consistent. The idea that we don't rely on perturbation theory or more generally approximations in order to yield solutions. Why do we want this in a fundamental theory? Well, there's a sentiment that these features imply, again, with what we had maths, people tend to interpret that as we're missing something physical. So there's a pretty strong assumption about my description of the world. It's not very philosophically justified this way. However, it's based on past success of physics as an enterprise. It's sort of the opposite sentiment, so people wonder about how physics can be so successful, our use of maths and physics can be so successful. But really, this sentiment is like the opposite. It's like we're taking it for granted that we can describe the world with philosophical theories and mathematically consistent ones. So I think it's not really past success here, because again, I think we could use a similar argument that use unification to show that it's not linked to success. It nevertheless seems like what physics is about. They're in business to try and make it usable for themselves. Finally, background independence, and I'm not talking about naturalness because I couldn't fit it in, but probably naturalness too. Background independence is the idea that no fixed structures across or models of the theory. There's nothing in the theory that needs to be specified by hand. Why do we want this in a fundamental theory? Well, if structures need to be specified, then they're not explained by the theory. So then we seek a more fundamental theory beyond that in order to explain these structures. There's also an argument that Ravelli makes for past success. We can view physics as increasingly more and more relational. Again, I think this needs a further argument. This explanation is the struggle one. Okay, so those were the conditions. Now I'll talk about quantum gravity and what it means for fundamentality. So, generally, as I've said, quantum gravity is supposed to be a quantum theory of space-time. Its motivations are explanation and unification. However, it's not necessarily a unified theory, and it's not necessarily a universal theory. So in the first case, we may have a semi-classical theory, which is non-unified. And secondly, it need not be a theory of everything, even at its own scale. It may just be a quantum theory of space-time. And this is okay, because as Niels and I argue, quantum gravity is not necessarily a fundamental theory. He's cringing so much. Alright, so now we'll look at string theory, which does proclaim to be a final theory. And it has two claims for this. Firstly, it's a theory of everything, so it's got universality and unification, and it's also UV complete. There's an argument for a minimal length, which comes from T-duality, the minimal length being string length. So it's UV complete. So it's got those two things going for it. But together, these aren't sufficient to overcome the epistemic worry and have us stop digging. David frames the epistemic worry again. If string theory were a viable framework, but only an effective theory, then this claim of minimal length would be a statement about physics beyond the domain where string theory applies. So this is a statement about what lies beyond the string scale, and thus could not be trusted because it addresses a regime where string theory is no longer valid. Thus, there could be a theory beyond, one that doesn't feature this minimal length scale. Again, we are not trapped in the framework of string theory. And again, there's arguments against this, which I'm not talking about today. But certainly doesn't believe this is the case. Alright, so David frames the epistemic worry in terms of empirical data. At any given time, he says, we cannot claim access to all possible data. And there's this worry that experiments will turn up something that we can't explain by our putatively fundamental theory. So this is harking back to the turn of the 20th century. There's a statement attributed to Lord Kelvin that there's nothing new to be discovered in physics. All that remains is more and more precise measurement. And we know what happened after that. Experiments turned up strange results that required new theories to be developed. However, Lord Kelvin wants to remind you that he didn't actually say this. It's misattributed. More likely, it's from Michelson. He's got a quote similar to that. Alright, so David then argues that this sentiment is no longer applicable in modern physics because non-empirical considerations are running forefront. And then he goes on to present his non-empirical argument. I agree with David on this point. I agree that the understanding of the epistemic worry of modern physics is no longer about empirical data, which is why I disagree with the way he formulates it in terms of empirical data. The worry now, I think, is not a fear about new data appearing. It's more generally the fear of missing any physics beyond. So it's equivalent. How's he supposed to laugh? That's the Black Friday sales.
Oh.
Where you're scared of missing out on the TV. Fear of missing out.
Oh.
Okay, it doesn't work in Switzerland. Alright. So, string theory does have those two conditions. However, it doesn't satisfy the other conditions of fundamentality. In particular, non-terminativity, naturalness, background independence, and by background independence and naturalness, I mean specification of the correct parameters for our world by some natural mechanism within the theory itself. And so string theorists themselves are still digging for a fundamental theory. However, the difference between them and everyone else is that they believe that they're in a final framework. And as I said, Dewey has arguments for this, which unfortunately I can't consider today, but these are obviously disputed by other people working in quantum gravity. Okay, so what can we conclude from there? I'll start with my kind of more dubious thing about the spirit of physics. So I've argued that there are some conditions on fundamental theory that require some pretty hefty assumptions about the world, or rather our description of it. For instance, this idea of unity rather than diversity, that it be mathematically tractable rather than messy and unusual. And these don't seem philosophically justified. They require further arguments, especially if we're relying on past success. Nevertheless, they seem to capture something very central to the enterprise of physics itself, which is that the world is everywhere amenable to physical description, and that this description is useful to us as far as it can be. So, I think as long as we're doing physics, this is just part of what it is to be doing physics. Otherwise, it does feel like you've kind of given up and you're doing something else. So this spirit of physics, I think, is a bit like the ghost of Christmas Past, reading Scrooge on an adventure. She may be a nebulous character, potentially leading us astray. But to give up on these sentiments seems to deny something central to physics itself. So she is Christmas. Also, you'll note that I've done all of this work from the perspective of physics itself. I've been asking what are the necessary conditions of fundamental theory according to physics. Okay. So the next conclusions are against the epistemic worry, so no FOMO, no fear of missing out. The main principles that I've said are based on this search for fundamentality, as well as the spirit of physics, is this idea of completeness. So completeness, I think, has two aspects to it. So firstly, it's full coverage. So UV completeness means that there's nothing beyond at any shorter distance scales. Universality means that there's nothing beyond at the scale that we formulated. And finally, we have this idea that in principle we can derive all physics at larger scales. So altogether, these three give us this full coverage idea. And the idea of full explanation is that there's nothing in the theory that apparently stands in need of explanation. But then FOMO jumps in, says, we can never know that there's something we're missing. What am I missing? So why not keep digging? And my suggestion is that we try to turn this attitude around. If we have a theory that fulfills all these apparently necessary conditions, even if we can't prove them sufficient, we ostensibly have no reason to keep digging and no motivation to think that it's something we're missing out on. So the burden now, I think, would be on the person who wants to keep digging. We ask her, why do you want to keep digging? And she'll either give us an answer, which we may then add to our list of necessary conditions, or it may just be this general fear, which I argue she's not motivated, not justified to worry about. So that's it. Thank you.
Looking for the fundamental theory.
So can we see them? Okay, that's a bit hard. Let's see some contours. Okay,
I should have warned you we were going to do that.
Alright, that's much better. So do you have questions?
Do you guys have questions?
I have a sort of comment question. In section 4, you claimed that you couldn't see a reason for there being multiple fundamental theories instead of just one. I think I can give a sort of argument for why there would need to be one instead of multiple. So imagine that you found two fundamental theories, but they're supposed to be fundamental physical theories. They're not just fundamental theories in general. Well, if they're supposed to unify all of the things that we experience in the universe, then shouldn't there be some, like the entities that those theories describe, some point at which they connect, some point at which you have empirical contact with us for both of those theories? And if that's the case, then shouldn't there be like rules of communication between the information that those theories are about? And if that's the case, then shouldn't you have, for any given theory 1 and theory 2 that are both in our universe that are empirically tractable, then you should have theory 3 that's just T1 plus T2 plus the communication rules. And then you would think that that theory is just the fundamental one. It's a little bit more messy looking, but it seems like it captures all the stuff. So then the alternative case is that there is no such T3. Well, then what does that mean? It means that one of these theories is not in contact with the other theory. There's no way to make empirical contact with it, which would just mean that it's about stuff that's not physical. At least not physical in the sense that like we can interact with it in any way. And so then you have a dualist universe, but that's not a physical theory that we care about. That's it. That's the end of the question.
Yeah, I like it. I think I agree with you. Just to clarify, though I think your statement is totally compatible with both ideas, when we have two fundamental theories, I don't mean that they're both describing the whole universe, it's that they're describing aspects that are fundamental, right? But I think that's what you're saying, if they match up, then we should have a theory kind of the boundaries, which seeks a new theory. So, yeah, I think I agree with you. I feel like that's kind of what we have with the standard model. So you can treat them as individual theories, or you can lump them together into the standard model. And I can't think what. Now I'm confused myself. But then there's kind of no difference between the theory altogether and the separate parts, as long as they link up, right? As long as they cover everything, you're not necessarily seeking a theory to be on unless you're wanting something more unifying.
I don't know, my intuitions have gone astray now, so. We can move on. I have no more clean thoughts to present about that.
Simon. Okay.
Other questions?
Sure. Okay. Hey, Karen, that was nice. So, maybe I kind of missed something in the setup, but my question was again about the way in which the criteria for fundamentality are motivated. So I guess Brandon was asking about the extent to which they're sort of motivated by whatever, unification and minimizing the sort of independent explanations. I was thinking more about the sort of past success kind of argument. Since we don't have a fundamental theory yet, I guess we haven't had any success at all in writing a fundamental theory down. So what is this success supposed to be that would make these criteria for a fundamental theory? Is it just because of relative fundamentality, or that was it? I mean, that's sort of appealed to, but obviously, right, it's not something we've ever succeeded doing, so how's that supposed to work?
Yeah, thanks. That's a really good point, actually. So I guess by past success, I just meant successful as being physical theories, not necessarily as being fundamental theories. But then there's this idea that they're getting more fundamental. So the more unified seems more fundamental than not. So maybe that's the idea. It's more successful as being a theory, but also getting at something deeper each time. What do you think?
But I thought the whole point was to get to criteria that would tell us when we actually got to the bottom, right? So that's just going to tell us we found another more fundamental thing, right? I mean, it couldn't tell us, and now it's fundamental because, right, the induction doesn't seem to go that way. It just says it's something more fundamental, what we should expect of more fundamental.
Yeah, right. So some of these conditions can be embodied by non-fundamental theories, the theory being non-conservative, for instance. But we don't have a theory that's fully universal and fully unified and it's satisfying all these conditions yet. So they're only kind of imperfect representations of these, of the full list, say. And the idea is that once you fully realize all of this, then we have a fundamental theory. Well, not a fundamental theory, a candidate for a fundamental theory, I should say. Because I still think it remains to be seen that these are sufficient.
Okay. So they're sort of, okay, the idea is they're sort of individually necessary, but maybe they can be jointly sufficient or something as well. Okay. I have some more questions about other things, but I can come back later. Do you? Okay. Nope. Take it away, Geneva.
Okay.
Thanks for this very sort of so a couple of times you mentioned you talked about those were the final maybe that struck me as a sort of concern for fundamentality. Well, yes, my idea is it was dependent on anything else and some other things. And so, UV completeness. It doesn't seem like completeness as special. My attitude from that. Then, if you only work on it, it won't be fine. So, you might be maybe adapting relative goals.
Yeah, normally I do distinguish between them, but not for the reason God said. So saying we could have two fundamental theories, only one final.
Well, those are fundamental, I guess, in the sense that neither of them depends on anything else. Most of them have things that depend on. So we sort of that's. But if you just have one of them, you do a second. You don't have to find it, you don't dump the physics. Walking up your eyes. Because that is something that one you have to find.
Yeah. Yeah. So I guess for this, I'm really talking about final theory. Yeah. So, but then I guess the same worry comes with a fundamental theory. How do we know it's not dependent?
Sure. Yes.
There's some of this.
Yeah.
Okay. Thanks. Yeah. I'll definitely fix this with the paper.
So maybe I can jump in because I think I have a similar idea or worry, which maybe also partly what Brand was trying to get at. So this is motivated by the possibility of dual theories, and maybe suggests that although the criteria you gave may be individually necessary, that they may not be even jointly sufficient, because it seems at least possible that we have two theories, maybe in some sense dual theories, which individually all check the conditions. So they're really complete, unified, non-perturbative, consistent, backward independent, natural universal theories. But there are two of them. Now what do we do? Well, if we take your list as sufficient conditions, we should stop digging. But maybe the very fact that we have more than one may be a motivation to dig for something deeper, somehow a theory that captures the same physics, but it's just one theory to get rid of the underdetermination.
Okay. So I was taking it that being unified plus being universalism means there's only one singular.
So there's no
But I think it doesn't really put it that way. So I should add to the list that there's just one.
I mean,
What's the sentiment of physics? They do just one. So.
I think so. I think even if we have two dual theories which are maximum in other ways, the fact that there are two alone, I think, might be motivation to keep digging.
Yeah.
And three of these things can have two.
Well, they may be formulated in very different mathematics.
Okay, so the answer
Well, okay. Then that's at least then
you know that's very definition that they are the same. What do you say? What do you say? They check everything, everything, everything.
No. They check the conditions here.
Okay.
So these conditions by themselves do not make a unique theory of the world, I don't think.
Maybe that is an interesting issue there of differences. And my question was related to your theory about the explanation. There is nothing else to explain, but it's small, or I don't know, is that how British does? Because what does it mean there is nothing else to explain? Because we always assume we will start from a set assumption to explain things, but then in some way, in logicians or other people can phrase this in a better way. You can always come to another set of assumptions, maybe possibly explain different ways of the same set of things, so that it's not clear that you get figured out, but see that question.
Maybe not. I mean, I understand this idea of nothing to explain is very, very.
Yeah, for instance, in one framework, you start with a set of assumptions, but then in another perspective, some of these assumptions can be explained, starting from others. So it's not clear how useful it's
Right. I need something like under perturbation to these assumptions. The theory is everything. Maybe different formulation of the same theory.
Okay. we have more questions, can I ask people to speak up loudly and clearly so that the microphone will transmit the questions to Chicago now? Please.
And slowly.
The talking are really important. Right? I mean, I also think that this point is nice and you should add to the list that there is only one unique stage. Because otherwise, you don't really know whether you should continue to dig or not. And since you don't know, you will dig, I think. So, I think we should have only one theory for
yeah. Because otherwise we're kind of wanting to explain why we have.
Although we don't really know what's happening, and since we don't know, we want to investigate, I guess. But the only thing I wanted to ask was about how you think about scales, and how exactly do you relate scales with fundamentality? Because at some point, I think you said that fundamentality was relative to scale, something like that. But then later in the talk, you said that you said that the fundamental theory has to cover all scales.
Yeah.
So I thought it was kind of conflicting.
So I was putting forward the idea that there is a case to be made that was fundamentally dependent on scale. But then I was putting that aside and saying, even though I'm sympathetic to that idea, I'm not using it now. Now I'm using this other idea that the short scale is more
But do you mean dependent on the particular scale? On one, I mean, is one of the scale more fundamental than the other scales?
Yeah, the idea is that we're seeking the deepest scale, the most bottom one.
So,
Yeah.
so in your view, fundamentality has to connect the smallest.
Do you guys have any more questions?
Personally, I'm not sure how I'm going after that because I do like this other idea. But for the sake of this talk and using kind of what physicists are using, this seems to be the more general sentiment there. So yes, I'm using it.
So there are more questions in Chicago.
Hey, it's me. Whoa. It's me again. I don't know if these are sort of questions, but I think there was a point where you asked about other sort of references where people had talked about these things. So I thought I'd mention a couple of those. I mean, on this question about unity and what you're talking about is a patchwork of laws. I don't think you mentioned Nancy Cartwright there, but I mean that picture is exactly what she's sort of argued in the fundamentalism versus the patchwork of laws. I mean that seems very sort of apropos. And you were, you're talking, and okay. There's not, and then also in response to the FOMOs, it always makes me think of Newton's third rule of reasoning in the book 3 of the Principia. Part of his point there is, what he's saying is you have no reason to sort of doubt the theory that you've, as he says, deduced from phenomena, unless you have some other phenomena that, either refute it or give you reasons to go beyond it. So he doesn't really give an argument for that, but people have sort of worked on his methodology. But if you at least want to make an appeal to authority to make that point against the FOMOs, you can't do much better than Newton, I would think. So that's not really a question, just a couple of, I guess regarding Cartwright, it's also true that, a lot of, I think the people who respond to it have responses along the lines that Brandon was making about, how can you really have a patchwork of laws at a single level? How are they? Because you have to sort of do something at the intersection of them. It's hard to see that there would be like sharp boundaries. There's going to be overlapping areas. So, yeah.
Cool. Yeah, thanks a lot. It's very good. I'll check it out.
Well, I have a quick.
Yeah, clarifying the boundary idea too. So that's it. I understood it when Brendan asked it, and then when I tried to And so I got a bit lost and ended up confusing everyone. But yeah, I think it's a really good point. So thanks again.
So I have one more question. So in section 5, in your discussion of string theory, you said that there was the FOMOers, those who thought, beyond that fundamental scale, there could be more physics to be discovered. So that alone might give us this fear of missing that physics, but give us reason to go deeper. And you seem to prove it there, even though maybe not on its own ground, but then because string theory doesn't satisfy some of the necessary conditions for fundamentality. But then, judging from your conclusion, you think, had it not been for not satisfying these other necessary conditions, you would not have agreed with FOMOers. You would have said, no, it's not a rational thing to do. I mean, because sorry. In the conclusion, you said just the fear of missing out, digging for the sake of digging, because we could find another lump of gold in there, perhaps. It is not enough to motivate or justify digging. So what justify digging in the case of string theory is because it doesn't satisfy these other conditions.
Exactly, right.
Okay.
So if string theory is successful in finding the fundamental theory that satisfies all these other conditions, then I'll be on board. And I think other people will then have to do some real work in justifying what they're not.
Okay, well, and then we should need to keep it. Thank you. I have one question, if I may. So this is also your discussion of Beat's discussion of string theory, and you didn't say much, except that you agree with him that there are non-empirical considerations that play a crucial, inevitable role. Would you care to elaborate a little bit? What do you agree with
Yeah.
specifically?
I think exactly. The very reason we're seeking the theory of quantum gravity is not because we have new data to explain it.
Okay.
It's because we want a new theory, and this is what's really motivating the search now in modern physics, contrasted with this case of the determinism, where it was motivated by strange books.
Okay, so it's not that you endorse his specific arguments that turn on non-empirical considerations.
No.
It's more generally that you accept that there are important non-empirical considerations motivating our thinking.
Yeah. So he says that the epistemic worry is a fear that we're going to turn out new data. And then he says, but this isn't how modern physics works now. So I agree with his point that this isn't how modern physics works now. And I think he should then rephrase this epistemic worry about is no longer about empirical data than that.
Good. Are there more questions in Chicago?
No, I don't. Nope, I don't think so. There were a couple of small things you said I might just write you an email about, but I think I see what's going on. Yeah, nice.
Yes, please. Do write to me, and all of you, if you have any more ideas, I really welcome them. And especially, I'll try and get these draft done. It's very short, the essay, and non-technical. I'd love to share it out with you. But maybe we should then start with the photo after the competition.
Cool.
Thanks.
I have one more question. You said one of the reasons for not considering GR fundamental is because it's, or some of its models contain singularities. And then you said that points to some sort of explanatory deficiency. I was wondering exactly what the deficiency is of those models.
It's just that there's, the domain that you
So is there such a domain?
according to the theory. Yes, really good question.
I don't mean to ask a weird question, but see, the letters are a little bit funny in GR, the global properties of the model. I mean, at least those who know about it.
Yeah.
It's maybe the way to phrase it in one side is that the domain where the theory is really applied.
Yeah.
The strict feeling it's not exactly the case that it's somewhere or I don't know, domain where the theory is really applied.
Right, so you can say, GR doesn't say, here's the domain, and oops, here an identifier or something like this. You know, here is the big bang or black hole. This is where I should give you an explanation or whatever, an account at least of well-defined physics, and I don't simply. But there's a sense in which these are not part of the model. They're not particular part of it. So in what sense is it? I mean, that doesn't mean there's no explanatory deficiency. And I think it's just not so. It's not so trivial really to say what the deficiency that is.
Yeah.
I see.
No, I agree.
Okay.
As I said, it's very high level to represent all of these ideas.
Of course. And
I'll definitely be more.
And it's certainly, you know, all of these things are things physicists say in print. And I bet money that there's no problem right there. Physicists, even quantum, to say things like this almost never.
We hold ourselves to higher standards here. I appreciate it.
Yes. These are the sort of things that philosophers really want to be very, very precise about. Maybe also connected to that, or the belief, the motivation for quantitative imperatives go beyond GR. You say that there's a requirement for a theory covering the domains where the field is set.
So that's not usually the way I phrase it in my paper. So I'd say the domains of necessity of both theories. So.
Right. Okay. I think that's better, yes.
Yeah.
Yeah, 5 more minutes.
Well, okay. I will say one of my other things. But I sort of feel we've talked about this before, and so maybe it was just a shorthand. So you said a couple of times that the longer length scale physics can be derived from the shorter length scale physics. But if derived really means sort of logically derived, or I'd say sort of even that the theory is supervenient, that I at least am skeptical that that's the way to put it. But I think maybe in the longer paper it's put more subtly than that the relationship between the different levels isn't just one of like derivation, right? Is that right? Or
yeah, exactly. So it's something that I really don't like, this idea of the claim that we can derive in principle. I think this kind of dependence claim is probably the best way of doing it, and maybe that's how I should present it in the paper itself. So just saying that the laws depend rather than being reducible or derivable. Definitely.
Okay. And that's another kind of that's a sort of vertical disunity rather than a horizontal disunity, which is what you're talking about. Okay. Yeah. Yeah.
Thank you.
I have another question. I'm sorry. So, on the one hand, we have quantum gravity and we have convincing arguments in that paper, for instance, that such a theory would neither have to be unified or universal and therefore not fundamental. So it may not check several of the boxes, of these conditions for fundamentality. That seems right to me. There's a good case to be made for that. But it would, if these conditions are necessary for fundamental theory, that would still motivate us then to keep digging.
Yeah.
Beyond quantum gravity.
Yeah, I agree with this.
Okay. So quantum gravity may be a step towards, on that digging, one of the pioneers show.
Yeah, exactly. And I think that might be the attitude of people working on other approaches. Although I'm not certain. It may be that they think that in terms that could have kind of this disjointed set of theories that universe make sense for them. So maybe they would not want this further condition on fundamentality that is maybe beginning, but I'm not certain.
Oh, so I see. So the idea would be that quantum gravity is not a non-fundamental theory. So there's no theory such that it is more fundamental relative to quantum theory of gravity. But the situation would be that quantum gravity is part of the fundamental theories, but of course not all of it.
Yeah. So my beginnings to the fundamental.
I think it's maybe final for its domain, as it were. But, yeah.
There's some wiggling here on maybe different sets of what people would it actually use. But I don't want to get too into. I think it's easier to just say we can conceive of it as not fundamental. Therefore, use it as a stepping stone.
Right, because, if you're then in a situation, suppose we have a quantum theory of gravity, and only of gravity, and we have to stack them all. The fact that maybe, even though maybe together they kind of exhaust physical phenomena, together they give us everything we need, still, the fact they're not, the set, the totality is not unified. So in that sense, the set doesn't satisfy all these conditions above, and maybe motivation to find some underlying theory that has a high degree of unification. So
yeah, exactly. Right. But so this is my thinking, yes. But I think there may be some quantum gravity theories that are happy with this first situation.
So, yeah.
But I think, yeah, it's definitely still the claim that we would see something more unified beyond that.
All right. Chicago, last chance for a question.
I think we're all good here.
All right. So please join me in thanking Karen again.
Bye. See you next week.
Bye-bye.